Hello and welcome again. In this video lecture we will be talking about Bode plots, an asymptotic frequency response plot technique that was developed back in the 40s by Hendrik Wade Bode, an American engineer, researcher, inventor, author, and scientist of Dutch ancestry. There's a page from Wikipedia and I'm just going to read a little bit about this gentleman. As a pioneer of modern control theory and electronic telecommunications, he revolutionized both the content and methodology of his chosen fields of research. He made important contributions to the design, guidance, and control of anti-aircraft systems during World War II, and continuing post-World War II during the Cold War with the design and control of missiles and anti-ballistic missiles. In addition, his research impacted many other engineering disciplines and laid the foundation for a diverse array of modern innovations such as computers, robots, and mobile phones, among others. Bode was one of the great engineering philosophers of his era. Long respected in academic circles worldwide, he is also widely known to modern engineering students, mainly for developing the asymptotic magnitude phase plot that bears his name, the Bode plot. His research contributions in particular were not only multidimensional, but far-reaching as well, extending as far as the U.S. space program. So we are very indebted to Mr. Bode for having developed this efficient technique for hand plotting the magnitude and phase versus frequency response of a system as described by its transfer function. And you might ask, in this day and age, why do we bother with developing a hand-drawn frequency response plot? And the answer is, well, partly there are different opportunities today. There are greater opportunities. Mr. Bode did not have computers readily available to him, at least ones that had a nice interface and that graphically could present results. And we do today. However, one of the great benefits of doing these plots by hand is that in the process of formatting the transfer function so that it can be readily plotted by hand, one gains insight into the system. And then when one draws the transfer function, these various asymptotic lines on the frequency scale, it reinforces and gives the engineer insight into the particular dynamics of the system, something that might be missed if the transfer function were simply plugged into a computer and the results graphed. I have such a computer program here that I'm going to, well, I already have it up here. We have a transfer function h of s that is equal to 20 times s plus 100 divided by s squared plus 10s plus 400. And below here is plotted the magnitude of that transfer function in red and the phase in blue. The red magnitude is scaled on the left side here. It's on a log scale, so we see powers of 10 ranging from 0.001 up to 100. And the frequency scales from 1 radian per second up to 10,000 radians per second. The phase response is scaled on the right and begins at 0 degrees and descends to minus 150 degrees. If you want an exact representation, then you will use something like MathCAD, MATLAB, even Excel to plot or generate these plots. However, oftentimes you just need an asymptotic straight line reconstruction or construction of such a plot. I'm now going to draw the asymptotic straight lines that correspond to this magnitude and phase versus frequency plot. The technique that we're going to develop, the Bode technique, will teach us how to produce these straight line approximations from which we can produce a pretty good estimate of the exact plots. Things that I pay attention to here are corner frequencies. That's wherever the magnitude response, that is the red or the orange graph, takes a change in slope. So we see one that occurs at 20 radians per second, and we see one that happens at around 60 radians per second. Let me just point out a few things, and this is just to give a kind of jump to the end, and then we'll come back and look at the actual technique in detail. So in red, we have the magnitude plot. We have a couple points here that I'm going to point out. We have, at this point here, we have a pole. In fact, we have a pole pair. There are two poles, and we have yet to define a pole, but essentially a pole is a zero in the denominator of the transfer function. And we have here a zero. So a pole pair is, these are two complex conjugate roots in the denominator. And a zero is in this case, it's a single real zero, so it's a one real root in the numerator. And we sometimes talk about these as breakpoints, because you can see that if we're drawing straight lines to approximate the magnitude response, at these, every time you encounter a pole or zero or a combination of them, it'd either be a single pole, a single zero, or a complex conjugate pair, there will be a breaking of the asymptotic line. It'll change its asymptotic slope. So in this region here, we have a slope of 0. In this range out here, we have a slope of what we call -1. It's -1 decade per decade. If you look here, we cross the 0.1 magnitude at a little above 200, and we're going to cross the 0.01 just above 2000. Right? And if I go further out away from this zero here, eventually this will be exact. In other words, for every factor of 10 that you'd increase in frequency, you will decrease in magnitude by a factor of 10. In this region here, it is a slope of -2 decades per decade. And of course, down at the low frequency, it's a slope of 0 decades per decade. And what we're going to do is to look at the transfer function and identify what are the dominant portions of that transfer function within any frequency range. So as we span from very low frequency to high frequency, and we usually do it in decades, we're usually looking over a wide range, many orders of magnitude, what dominates the magnitude of that transfer function, and then we're going to approximate it as a straight line. And then we connect all the straight lines together. And finally, after we've connected all the straight lines together, we recognize that, well, whenever you do have a breakpoint, such as this 0 here, or the complex conjugate pole there, that the actual magnitude curve doesn't follow those asymptotic lines exactly. It deviates some around those breakpoints, and then we'll develop a few techniques on determining how we do that and how we estimate that deviation. Phase response is going to be plotted on a linear scale vertically, but still a log scale on the frequency axis. And we see that there is an asymptotic phase that is associated with each section here of our frequency response plot. So for instance, in this region here, when we have a slope of 0, we have an asymptotic angle of 0 degrees. So a 0 decade per decade has no phase shift. And that should make sense. If your gain is changing as 0 per decade, it means that there is no frequency component. It would just be some constant k. So maybe your transfer function would be 5. Right? And what is the phase of 5? It's 0. And so here it's going to be 0 degrees per decade. Now we could have the case where we had a gain of -5, in which case the phase would be not 0, but it would be 180. But again, it's not changing. So it's 180 and it's always 180. If we have a slope of -1, so in this region here and on out, we would have minus, the asymptotic value here is minus 90 degrees. So as the magnitude slope converges with this -1 decade per decade slope, as we go further out in frequency, the phase is going to settle out at -90. If, on the other hand, it has a slope of -2, like in this middle section here, all right, if we never had encountered this 0, but we just continued coming down at the slope, or the magnitude response continuing down at this rate, then the asymptotic phase would have been -180. Okay, and we find that we will have 90 degrees asymptotically per, I should say plus or minus, 90 degrees per degree of slope. So for instance, with a slope of 0, we would have, these are asymptotic values now, a slope of 0, the asymptotic phase would be 0, or we could have 180 degrees. You can kind of always throw in, add or subtract 180 depending if there's a sign thrown on at the front. If the slope is -1, so we're decreasing by a decade per decade, then the phase asymptotically would be -90 degrees. If it was +1, in other words, if the slope, magnitude slope was going up at a +1 slope, then we'd have +90. If it was -2, as it is in this region right here, then we'd have asymptotically -180. If it was +2, we'd have +180. And you can see that it's essentially 90 times the order n, where this would be n. So the approach we're going to use, and I realize this may seem a little foreign and confusing, and that's okay. We're going to come back and look at some examples, but I wanted to give you a kind of a big picture view first at what this technique will look like, and let you know that we are going to work on being able to construct this magnitude response curve, the red one, by first identifying the different breakpoints, the poles and zeros, and the asymptotic magnitudes that accompany those, and then from the magnitude response plot, using this relationship, I should say specifically this one, that the asymptotic phase is 90 degrees times n, where n is the asymptotic slope of the magnitude curve, we can then construct the phase response. And we generally can do a little better job on accurately or more representatively capturing the magnitude response than the phase, because the phase response it changes over a larger range of frequency. We'll see that, but nevertheless, you can definitely accurately predict the asymptotic values and reasonably predict the values in between. And it's somewhat of a function of how close your various breakpoints are. If things are really spread out, then you can draw it very accurately. If you have a lot of breakpoints close together, and as an example here, this pole here, double pole, and then this 0, they're pretty close together. Why do I say they're pretty close? Well, they're within the same decade. And everything, when we talk about close or far, in the area of plotting frequency response, we're talking about relative to orders of magnitude. So close is anything that's on the order of magnitude one with the other. Large is when you have at least an order of magnitude separating the two values. Okay, now we're going to actually begin kind of the nuts and bolts. So we're going to use this transfer function we'll call g of gs. And in general, a transfer function can be written, it is a ratio of two polynomials in S. In the most general form, we would write something like b sub m, that's some coefficient, times s raised to the m power, plus b sub m minus 1, s to the m minus 1, and we could go on all the way down to b sub 1, s to the first, b sub 0, s to the 0, which is just 1, and divided by, same thing in the denominator, except we use different coefficients, a sub n, s to the n, and we'll say the order, we'll say m is the order of numerator, and n is the order of denominator. These are not generally going to be the same. And this is the fancy kind of theoretical way. If you want to impress or confuse your friends, write it this way. Okay, but in general, or more compactly, we can just say we have a polynomial in S, call it ns, divided by a polynomial in D, in S, call it d of S for the denominator. And where those are each defined by the terms above, and we should stipulate that a sub I and b sub I, in other words, all of the coefficients above, are real valued. That's a reasonable thing to claim because, after all, these coefficients are going to come about by writing equations of motion of a physical system, and those coefficients will ultimately be tied back to properties of the system like mass and spring constant and capacitance, resistance, fluid compliance and temperature, things like that. So it should be real valued if we're modeling real systems. We can further describe this transfer function as having multiple or subproduct terms in each the numerator and the denominator. I'll give an example of this in a second here. So let's consider the example that we would have g of s is equal to, let's say, s squared plus 3s, and here we had 4s. Okay, well, I could factor that into 4. Now this may seem silly, but it'll make a little more sense in a few minutes. I can factor this into 2 terms in the numerator, 2 terms in the denominator. Another example might be 3 over s squared plus 3s plus 2. Here we can factor this into s plus 1 times s plus 2. All right, and so this would be our d1 and d2. Now, if we had, suppose a third transfer function, in this case, let's say it's 1 over s squared plus 2s plus 100. Now, looking at that, because of the size of the 0th order term compared to the middle term, I'm certain this has complex roots, and so let's use the quadratic formula to get the roots of the denominator. That will be minus b plus or minus square root of b squared minus 4ac divided by 2a. And this will be minus 1 plus or minus, and then we'll have 1 minus 100, or minus 99, or j 99. So we have complex conjugate roots. Now we could, in fact, factor that into s plus minus 1 plus j square root of 99 times s plus minus 1 minus j root of 99. And we could say this is d1 and d2, but we will see that this is not profitable. When we have complex conjugate roots, we are not going to factor the quadratic term, and we're going to leave it as a quadratic term. And so that's why the number of subterms that you would have, the d1, d2, d3, is not necessarily equal to n, the number, the actual order. So in this example, we have the denominator has an order of 2 because the highest power of s is 2, and yet we are not going to factor the denominator into two subterms, d1 and d2. We're going to leave it as just a single term. Okay, that brings up the types of terms that n1 and n, or n and, let's say, n sub I and d sub I, oops, can be of, will be one of three forms. Okay, one, we've already seen we could have constant. Okay, constant k. Second case, we could have simple real pole. I won't say pole, I'll say root, because this could be in the numerator or denominator. So this in general is like s plus a. And 3, we would have complex conjugate root pair. Complex conjugate, and they always will be complex conjugate if they're the unfactored quadratic is real valued in its coefficients. Complex conjugate root pair. And in this case, we would have s squared plus bs plus c. And what we're going to do now is to look at each one of those terms and consider how we can plot their magnitude and their phase versus frequency, and how we can do that by hand. The important point here is that once you can plot these three types of terms, you can plot any transfer function. Now, before we go into looking at each one of those terms, let me explain, or to show that that is in fact the case, that by being able to plot each of these individually, you can then construct an entire transfer function. So I'm going to claim that the magnitude, let's say if, first of all, if g of s is equal to n of s over d of s, which is equal to n1 of s, n2 of s, and let's just say it's got 3 terms here. No, I'll just leave it. d1 of s, d2 of s, dot, dot, dot. Then I'm going to claim that the magnitude of the transfer function, and here I'm using j omega, not s. Don't let that confuse you. We generally, when we construct the transfer function, which is coming from some process of writing the equations of motion for whatever our system is, and usually it's involving describing, combining the impedances of different elements of the system, or maybe we have, if you know Laplace transform, you may take the Laplace transform of the differential equation, which turns all the derivatives into powers of s. However you get to it, eventually you're going to have this transfer function that is a function of s. But when we talk about frequency response plots, we are talking or restricting ourselves to the case where we are exciting the real system with real sinusoidal signals, like sine omega t's, cosine omega t's. And in that case, those type of signals are constructed by e to the j omega t. In other words, a cosine omega t, for instance, according to Euler's formula, is decomposed as being e to the j or I omega t plus e to the minus j omega t, all divided by 2. So we're using terms of the form e to the st, that is the excitation, and that's where the s comes in when we write our transfer function. But when we restrict ourselves to exciting the system with sinusoidal signals, we are restricting the values of s to j omega. And so I don't like carrying the j omega throughout the entire derivation of the transfer function because it's clunky. So I leave s, and then we just plug in j omega at the point that we're looking for the magnitude or the phase. Notice that if we don't assign s to its ultimate form, such as j omega, and we try to evaluate the magnitude, we can't, because to calculate the magnitude, we need to know which parts of the what the contribution is of real term and what the contribution in imaginary term is, and those are in quadrature, right? So you end up, to determine the magnitude, you take the square root of the sum of the squares. So we have to assign s to whatever its ultimate form is. We can't just say it's complex. We have to know how much real and how much imaginary there is in it. So I'm going to claim that the magnitude of the overall transfer function is equal to the magnitude of n of j omega divided by the magnitude of d of j omega. And furthermore, I'm going to claim that this is equal to the magnitude of n1. I'll leave off the j omega here, but it's implied. n1 of j omega times the magnitude of n2 j omega times ... however many subterms I have, and subfactors, and then divided by the magnitude of d1 of j omega times d2 of j omega ... So you see from the for the magnitude response, if I can efficiently determine and plot the magnitude of my three types of terms, then I'm just going to assemble those when I calculate the overall transfer function. It's even further simplified than this, though, because you might still say, oh, taking quotients and products is going to be complicated, nasty business, at least for a hand computation. And that's where drawing these plots on a log scale really comes in handy. So let me at this point introduce the decibel. The decibel was developed or defined back in the 1920s at Bell Laboratories, and is named in honor of Alexander Graham Bell. And it was used initially when they were stringing telephone cables across the continent. They were trying to measure losses in the cable, ultimately losses, hearing losses. So when you're at the other end, the volume is reduced. And so a decibel is a means to quantify typically a quantity of power or intensity relative to some reference or assumed or implied reference level of power. So the definition is as follows. Decibel is equal to, let me see, decibel of A, some quantity A, is equal to 10 times the log base 10 of A, and let me write this as A over AR, A over AR, where AR is the reference level. Okay, so, and if these were quantities of power, which they would be, so we might have, say, if we had 1 milliwatt was our reference level, then 1 watt would, if we were trying to represent 1 watt in decibels, we would take the ratio between 1 watt and a milliwatt, that would be 1,000. Take the log base 10, that would be 3, and this would evaluate to 30 decibels. And we might say 30 dBm. Sometimes they'll actually throw on some units there where M would be for milliwatt. So this is telling you that the particular quantity A, power A, has a power level of 30 dBm. It's 30 dB above our reference level of 1 milliwatt. And each 10 decibels represents an order of magnitude. So we're 3 orders of magnitude greater than our reference level, which is in this case a milliwatt. So 3 orders of magnitude greater than a milliwatt is a watt. Now, we will define the decibel as 10 times log base 10 for power quantities. So power quantities, we'll have the decibel is equal to, or the decibel of, let me just write it this way, dB of some power quantity P. I really should say ratio, I guess, is equal to 10 times log base 10 of that quantity. Now we also have what we call field quantities, and that's what we're going to be using. And this would be things like voltage, current, force, velocity. So it's essentially effort or flow. All right. For any of these variables, we will define the decibel as 20 times log base 10 of that quantity. And why is that? Well, let's consider, let's consider a resistor, okay, where we would have some voltage VR across that resistor. We would describe that resistor as having a power dissipation equal to V squared over R, right? V squared over R. And if I wanted to represent the power in decibels, I would say dB of the power of the resistor, and let's say I'm going to do it with reference to 1 milliwatt. Okay, so, or let's say to 1 watt. I'd say it's 10 log base 10 of 1 over R VR squared, right, divided by 1 watt, but that's a little superfluous. Now I can rewrite this as, I can bring the power of 2 out. Well, what I can do first actually is I can write 10 log of 1 over R plus 10 log of V sub R squared. And this can be rewritten as, I can pull the power of 2 out and write it as 20 log of my voltage. This is where the 20 comes from. The idea is that power typically calculated as the square, or being proportional to the square of some field quantity. Like in a resistor, it's V squared over R, or it's I squared times R. Similarly, for if it was a viscous damper, air drag, it would be proportional, the power loss would be proportional to velocity squared, or flow, or force squared, or torque squared, etc. And so the convention is that when we are representing some field quantity in decibels, we will use 20 times the log of that quantity. Now, when we go back to looking at the transfer function, we are representing, the transfer function is not a power quantity. It is not expressing, for instance, the output power with reference relative to some input power. It is expressing the output voltage or current, in other words, effort or flow, i.e. a field quantity, relative to some reference field quantity, which happens to be the input, right? What we're driving at the input. Therefore, for our case, for transfer functions that relate field quantities, such as voltage, current, velocity, force, temperature, pressure, etc., we will define dB of some, say, our magnitude of our transfer function, okay, as being equal to 20 times log base 10 of that transfer function. Now you may say, well, where's the ratio? There's no ratio. Well, by definition, the transfer function is a ratio already. It's a response with respect to a reference level, which is our input. Okay, now we can return to what we had written a little ways back, which is G of S is equal to N of S over D of S. And now if I take the decibel value of G of j omega, magnitude of G of j omega, I can write the following: 20 times the log of magnitude of N j omega divided by magnitude of G j omega, right? And doing some logarithmetic, I can write that as 20 log of N of j omega magnitude minus 20 log of D magnitude of D j omega. In fact, I can write this as being, well, let me rewrite that. I can write that as dB of N j omega minus dB of D of j omega. And we can expand this further and claim that it's going to be dB of, let me change the notation a little bit. Hopefully it'll be clear. I can write this as N in dB minus D in dB. All right, that's just the magnitude of the numerator in decibels minus the magnitude of the denominator. And I can further break this down to being N1 in dB plus N2 in dB plus ... minus D1 in decibels minus D2 in decibels minus ... And so thanks to plotting the magnitude on a log scale via using the decibel, the unit of, or the scaling of decibels, we can construct the overall magnitude, decimal magnitude of the transfer function by simply adding and subtracting the decibel magnitude of each of the numerator and denominator terms. So if I go all the way back to where we had started from here, claiming that if you know how to plot these three types of terms, constant term, simple root, and complex conjugate root, then you can very readily plot the overall magnitude of g of j omega. Now you can see why. Because if you can plot these three different types of terms by hand on a log, on the decimal versus, we haven't yet looked at the log frequency, but we're going to use log frequency scale. So if we plot decimal on the vertical versus frequency, log frequency on the horizontal, arriving at the overall transfer function, magnitude is simply a matter of adding and subtracting the magnitudes, the log magnitudes of the individual terms. Now let's look at phase. All right. In other words, I'm going to claim again that determining the phase of the overall transfer function g of j omega is readily done by simply combining the phases of each of the numerator and denominator terms. In fact, I'm going to claim that this is equal to the angle of the numerator minus the angle of the denominator, which further can be expressed as the angle of n1 of j omega plus angle of n2 of j omega plus dot 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 minus angle of d1 j omega minus angle of d2 j omega minus dot dot dot. And how can we show that? Well, I don't know if I'll completely satisfy your reasoning, but let me show one example here. Consider the number a plus jb. All right, so let's suppose that n was equal to a plus jb. No, let's say d was equal to a plus jb. In other words, I've got g of s equal 1 over a plus jb. Now I have g of j omega. Let's do it this way. I'll leave omega in there, okay? So g j omega is equal to 1 over a plus j omega. And let me do a little arithmetic on it. Let's multiply this by a minus j omega over 1, or a minus j omega, and let's complete the square on the bottom. So we'll have a minus j omega on the top, and on the bottom we'll have a squared. The cross terms cancel because of the sign, and we'll end up with j omega times minus j omega, and of course minus j times j is 1, so we end up with omega squared. So we have this, a over a squared plus omega squared minus omega over, well, let me just, actually, let's redo it this way. We have 1 over a squared plus omega squared, that's a real number, times a minus j omega. Now this scalar out front does not contribute to the phase. If I'm asking now, what is angle of g of j omega? The angle in this case is simply equal to, I mean, if I were to plot this on a real versus imaginary scale, I'm simply going to have something like this, where this will be, call this number k, all right, this term k, and it's k of omega, it's some function of omega. So I will have a times k of omega for my horizontal, and for my vertical term I will have omega times k of omega, right? And the angle here, which is the argument of my transfer function, or this is equal to angle of G, is simply the arctan of the imaginary over the real part, which is, in this case, just arctan of, what's my imaginary part? It's minus omega. What's going on here? Minus omega over A. It is equal to minus A tan of omega over A. Now, if I were to consider, what is the angle of A plus j omega, right? Which is, remember from up here, that's my numerator. Okay, angle of n of j omega is angle of A plus j omega. What is that? That is the arctan of the imaginary part divided by the real part. Notice these are the same. This is equal to the phase of the overall transfer function is equal to minus the angle of the numerator, which is exactly what I had claimed right here, that you could calculate the angle of the overall transfer function by taking the difference between the angle of the numerator and the angle of the denominator. We now are ready, finally, to embark on considering how we plot each of these terms.